Hello, my name is Liz.
And I'm Charlie. We both work for the NRICH project at the University of Cambridge. Now, the NRICH project was set up to offer students and teachers activities, resources, problems that encourage students to work mathematically. Now, we all appreciate and understand the importance, the value of students understanding the topics in the curriculum. So the content of the curriculum, of schemes of work, is incredibly important. And for many years, we've been publishing problems linked to the different areas of the curriculum. But it's also important to notice that for students to work like mathematicians, to think like mathematicians, to become good problem solvers, it's not just that content knowledge, the conceptual understanding, the procedural fluency that's required. They also need to be introduced to ways of thinking, to mathematical skills, the way that mathematicians think and work through problems. And with this in mind, we've been thinking about key skills on a problem-solving journey. And it's the 5 skills that we have identified as really important are the ones that we're going to be focusing on in this series of webinars. Liz, do you want to say something about that mathematical journey that we're hoping students will take?
Of course, yes. So we're imagining that students are being given a problem that they've never seen before, so that they're offered a problem for the first time. And at that initial stage, we want to give them an opportunity to work in a messy way, potentially, to try things out. We have called it exploring and noticing. So it's important to acknowledge that this may not look neat in their mathematics books, but we really want to give them an opportunity to get into the problem. Perhaps they'd be working alongside other people, and as they work, they may begin to notice some things.
Yes, it's important to have a culture in the classroom that avoid students being anxious because they're not quite sure how to proceed. This initial stage is the one that we all go through when we come across a problem that we've never seen before. Like you say, getting your hands dirty. But this then may lead to a slightly more organized, more systematic way of working, which is what we've called that second stage in this journey, working systematically. And by working in a more organized way, by perhaps keeping a record of results, students are much more likely to notice what's going on, whether they be noticing patterns or noticing results. The small changes and what the effect of small changes is can often be quite illuminating.
Absolutely. So then that leads us into the third phase where we're beginning to do some conjecturing. So we're taking some of the results, some of our noticings, if you like, and we're wondering whether if things are always going to happen that way. So this leads us to a conjecture. Is this going to be this way? And what happens in a more general sense?
If our conjectures are confirmed, if we've tested our conjectures with a few more examples, and we begin to think that actually there is something general going on, we may want to try and explain why it happens. So it's not good enough just saying, oh, well, this always happens, and then walk away from it. Trying to get a sense of why something is happening. And in order to do this, sometimes diagrammatic, visual representations can be quite useful. Sometimes algebraic way of expressing what's going on can shed light on what's going on. Sometimes analogies can be really useful. So this fourth stage we've called visualizing and representing. It's a stage where we're trying to make sense of what's going on.
And then we might have convinced ourselves that we are understanding the mathematics. However, can we convince a friend, or can we convince somebody who's perhaps a little bit more sceptical? And that's where we lead into the final stage, which is about reasoning, convincing and proof. So can I construct a very rigorous mathematical argument to convince a skeptic that this is always going to be the case? And in some cases, that may lead to a mathematical proof.
Yes, and even if we're not generalising, justifying why the strategy that we've used to solve a problem is mathematically rigorous is really, really important.
Absolutely.
Now, we're going to be discussing each of the 5 stages in this problem-solving journey in turn. And for each of them, we're going to choose an NRICH problem to be able to describe what we have in mind. Now, what we hope you'll notice is the problems that we've chosen are all have the characteristic of being low threshold, high ceiling. So low threshold means they're accessible, easy to step into. High ceiling because they offer the opportunity of asking more demanding questions, adding complexity to the original situation. And we try and produce problems of this sort because we think that all children are capable of thinking and working like mathematicians. So we don't know what the ceiling is that they can reach, but we make sure that all our problems are sufficiently accessible that everybody can make a start. Hopefully, this will whet your appetite for using some of these problems with your students. But most importantly, we hope that the guidance that we're offering will help you help your students become better problem solving, more confident mathematicians.
With that in mind, we've organised the NRICH website so that it'll be easy for you to find the resources that you're looking for and the guidance that we've written. So this is the homepage of NRICH, and if I look at the teacher's menu here, I can choose either primary or secondary landing page. Both of them are structured in the same way. So here's the primary teacher's landing page, and you can see on the left here there is a box which will take us to curriculum linked problems. So if you would like to find tasks organised by the curriculum area, this would be the place for you to go. And in a completely identical way, here is the curriculum linked problems box on the secondary teacher landing page. Equally, if you'd like to help nurture your students' positive attitudes and mathematical mindsets, then you click on this third box. This is the secondary teacher landing page, but as we say, the primary teacher landing page is structured the same. This middle box here, it will take you to all our guidance and groups of tasks to help you develop mathematical thinking skills in the way that we've described. Clicking on any of these 5 will take you to our written guidance and groups of tasks organised by year group so that you can be confident that you can find activities for the classroom which suit the students that you're working with. So let's think about this first phase in the mathematical journey, which we begin with exploring and noticing. So at NRICH, we would advocate you starting your lesson with a problem. Rather than assuming that students just need to pay attention, this is about having faith that students bring their own knowledge to the table and can work together to further their thinking and their understanding. They might do some pair work, and this is going to involve some messy playing around together. To illustrate this, we're going to introduce a game which is called Got It. Together to start with, Charlie and I are going to simulate what might happen in the classroom. So your students may well be playing against each other, either using this interactivity or on pencil and paper, for example. So Charlie, let's have a go at the game. So we're going to take it in turns to choose either a 1, a 2, a 3 or a 4. And whatever I choose is going to get added onto what you've chosen. The cumulative total we're making is going to get bigger and bigger. And the winner is whichever one of us reaches the target of 23 exactly.
Okay.
So I'm going to be kind and let you go first.
Okay, well, we both know what's going to happen here. But so what students might do is, I don't know, start with the number 4, for example.
Okay. And then, I don't know. At this stage, it's all, as we say, it's messy. I don't really know what's going to happen. I'm just going to choose a 1. We've got to 5.
But I want students to not be scared of trying.
Absolutely.
I don't want them to think that they need to get the answer and work out a winning strategy from at the very first moment.
That's right.
Okay.
Or that they need to do that quickly. This is not about doing it quickly.
Okay.
What are you going to choose?
Okay, I'll choose 3 this time.
Great. Okay. Oh, I might choose a 2.
I'll choose 4 again.
10. All right, we've got up to 4. Okay, that's taken us to 14. Okay, we're getting closer. Maybe I'm going to go for 3. That takes us to 17.
Okay, I'm going to choose 1
Okay.
because I know that if I land on 18, I'll be able to win. So at some stage, students are going to get to this.
At some stage they will. We've got there extremely quickly.
What would you expect students to notice, Liz,
Okay, well,
when they get to 18?
So at this point now, I noticed that the difference between 23 and 18 is 5. And actually, I only have numbers 1, 2, 3 and 4. So whatever I choose is not going to be big enough to get to 23. And I know that, assuming you are playing strategically, you will be able to get 23. So if I choose 1...
I'm going to piggyback on that, and I'm going to choose 4.
Whereas if I chose 2...
I'm going to piggyback on that, and I'm going to choose 3.
And if I chose 3...
I'm going to piggyback on that and choose 2. So whatever you choose, added to what I choose, make up 5.
Okay.
And I'll be able to get to 23.
Yeah.
So that's one realization that we want students to have.
Okay.
And that tends to come quite early on.
Yeah.
And at that stage, they think, oh, I've got a winning strategy.
Right.
I get to 18 and I win. And you might challenge them to play against a computer, and they might find that actually they don't win that easily. Because in order to get to 18, they must stop the computer getting to 13. So here's yet another noticing. And why 13 is so important is that it's 5 away from 18. And if the computer lands on 13, we cannot get to 18 in one go. And the computer will piggyback on our number. And so there is a lot of sort of exploring, noticing something, trying to make use of it, noticing that that's not enough, noticing that 13 becomes significant, playing again, feeling, oh, I've got a winning strategy, or challenging the teacher to a game. Yeah. We know the strategy. Realizing that actually it's not so easy to get to 13 if the computer's got to 8, and so on and so forth. But eventually working out that if you start with 3 and you always piggyback on the computer's number and go up in 5s, hitting 3, 8, 13, 18, you'll be able to beat the computer. But that realization comes after a lot of messy exploring, losing and losing before you can eventually come up with a strategy. Absolutely. And it's really important that students have that experience in a maths lesson, that knowledge comes after a little bit of hard work, a little bit of taking the wrong turn, a bit of testing ideas out. You're not expected to get things right for the word go.
That's right.
Now, we talked a little bit about low threshold, high ceiling, meaning that you start with a problem that's accessible and then you make it harder. Yeah. Well, you can make this slightly harder by changing the target number. But one interesting question is it always best to start? So if you had a target of 25, for example, and challenge students to play this and offer them the chance to start, again, they would notice that actually it's best not to start. So yet another realization, but that comes after sort of playing the game a few times and realizing that sometimes it's best not to start. And there are general rules about when is it best to start and when isn't it best to start. You can change the target, you can also change the numbers that you can use. Yes. So you can extend this problem, and at each stage, as you increase the challenge, there'll be the need to do a bit more exploring, new noticings. Eventually, it'd be quite nice to have a rule where you get given any target and any set of numbers, and you can tell whether you want to start or not, and if you start, you want to know what number to start with.
Absolutely.
Wow.
The power of mathematics.
But this comes after a few lessons, perhaps.
Absolutely.
Not after 5 minutes.
Absolutely, absolutely.
And it's really important that students have that experience. I remember somebody talking about mathematics is like climbing mountains rather than skipping over molehills. There's so much more satisfaction in getting to the top of the mountain, which has required quite a lot of effort. But when you get to the top of the mountain, you've got a fantastic view. So you and I know that if we've got the numbers 1 to 4, and the target is 42,567,742, would you want to start? Or
I would want to start. I'd want to start with 2.
And knowing that,
it's a powerful feeling.
Being able to say it with that confidence is something that is the experience we want our students to have.
Absolutely, absolutely. So we hope that's whet your appetite. If you would like to find out a bit more about how you can encourage your students to do some exploration and some noticing, then if you go to either the primary teacher landing page or the secondary teacher landing page and follow the link to developing mathematical thinking, you will see that there is a link to exploring and noticing. And right at the top in that blue box, if you click there, you're taken to our guidance page where we've given you some of our background thinking about this, including setting out our values about mathematics and mathematics education and what that might mean in terms of the structural considerations in your classroom. So perhaps the way you set up the classroom in a practical sense, or some of the ways that you organise students to work. And that leads in then into some prompts for you to use in the classroom to particularly help students to explore as they're working on a problem. If we scroll down a bit further, you'll also find some follow-up reading. I'm just going to go back a stage to the exploring and noticing page, and if I scroll down further beyond the link to the guidance, you'll see that what we've also done is gather together a range of tasks at each year group. So these are curriculum tasks, but for particular year groups, which will offer you some tasks to look at with your students, depending on their experience. And we know that these tasks will present opportunities for students to explore and notice.
And the problems on the screen right now are from the secondary collection, and there's an identical collection on the primary landing page.
Absolutely. And now we'll move on to working systematically, which is the second phase of our problem-solving journey. So we've reached the second phase in our problem-solving journey. We might have started by doing some exploring of the task itself. And now we've got to the stage, Charlie, where we'd like to perhaps make it easier for ourselves to notice some patterns. And one way we can do this is by ordering our work, structuring it a bit better. And by doing that, working in a systematic way, those patterns will become more apparent. So we'd like to share a task with you. This task is called the number jumbler. You may like to join in yourself as Charlie and I are demonstrating how it works. So we're going to begin by choosing a 2-digit number. And so it can be anything from 10 to 99 inclusive. And what we'd like you to do is to add together the digits of your number. So, for example, if I chose 42, I would add together the 4 and the 2 to make 6. And then we'd like you to subtract that sum from your original number. So in my case, I would take 6 from 42. And you should find that the results of your subtraction is on the grid here. And we'd like you to focus on the image to the right of the number you're thinking of.
So you're imagining that you would be doing this for the whole class?
That's right.
You'd be asking students all to be carrying out that little mental calculation for themselves, and all of them focusing on this grid.
Yep. And then I'm going to jumble up the symbols.
Which is why it's called the number jumbler.
Which is why it's called the number jumbler. And out pops a heart.
And if our students haven't made any mistakes adding or subtracting, there should be a, or wow. Well, how did that happen? Because all of them should have been looking at a heart, including you.
If you've not thought about this problem before, or you've not seen it, you may like to pause and have a bit of a think yourself before restarting this video.
So this might lead to a conversation about what do you think mathematicians do next.
Absolutely.
They might suggest they want to have another go.
Yep.
And we could have another go. I'm just going to refresh the screen. And you can imagine having another go. What's interesting is that if the students have another go, this time they're not going to get a heart when they carry out their calculation. So their original conjecture may not be quite valid. And they may do this 2 or 3 more times, perhaps.
Yes.
You may want to start recording, or they may want to start recording some of the results that they get. But really, there are so many different possible starting points that it is very, very time consuming to try everything out. So this is a lovely opportunity to get students to collaborate and work systematically.
Absolutely.
So one option is to split the class up into 9 different groups. Ask each group to work on sets of 10. So one group could be working starting with a number in the 20s. Another group could be starting with numbers in the 50s, and another in the 60s. And one group could be starting with the numbers in the 90s. And see what happens when they change, when they try all those numbers. And when you bring them together and they report back, they'll report that if they started with the 20s, like 24, for example, 2 plus 4 is 6, 24 minus 6 is 18. If they started with 25, 2 plus 5 is 7, 25 minus 7 is also 18. If it started with 26, 2 plus 6 is 8, 26 minus 8 is also... Actually, whatever number you start with, if it's in the 20s, you're going to end up with an 18. Whereas if it's in the 30s, you always end up with 27. If you started with number in the with the number in the 40s, you end up with 36. And all of a sudden, it becomes much more evident that you're always going to end up with a multiple of 9.
Absolutely. Now, at this point, we ought to say we haven't done any explaining. We've literally noticed this pattern, and by working systematically, it's become very evident that it looks like it's always the case we get a multiple of 9. But there's more work to be done, and we'll think about those stages of the journey further along. So we might move now into some conjecturing and generalising.
Yes, it could be tempting to finish here.
It could.
But we really don't want students to leave our classroom thinking maths is kind of magic. Magic in a, I don't know, I understand what on earth is going on. I don't want it to be in that. I mean, I wanted them to think that it's magic in terms of, wow.
Exciting, exhilarating.
Powerful, and so on.
Yeah.
I can do amazing things, kind of magical. But not in terms of, there's no way I can make sense of
Not
this.
Mysterious.
And so I don't want this to be the end of the journey. I want to carry on at a later stage, explaining, thinking about place value, maybe thinking about representing numbers algebraically to appreciate what's going on. But at this stage, working systematically has been really powerful because it has led us to see to an appreciation of what's going on and why we were all getting the same image.
Absolutely. So if you'd like to find out more about helping your students work more systematically, if you go to the primary teacher or secondary teacher landing page on the NRICH website, click in this second box, Developing Mathematical Thinking, and you will find you can click on the Working Systematically link. At the very top of this page in the blue box, you've got a link to our guidance where we have set out our thinking about working systematically and different purposes for working systematically, making the small adjustments we've just been describing. But you can see here that we've linked to a number of NRICH tasks at all different age ranges, so you can help your students develop this skill. If I scroll right to the end, I'll also find some general further reading. And to remind you, going back to that working systematically top level page, I happen to be on the primary teachers page, so here you can see we've got groups of tasks which are linked to the curriculum for years 1 to 6, so you can make sure you choose an example that best suits your students. So from here, we will go on to the third stage in our mathematical thinking journey, and that will take us to conjecturing and generalising. So we've reached the third stage of our mathematical thinking journey. We've done some exploring and noticing, which has led to some more systematic working, and now we've reached the stage where we can begin to do some conjecturing and some generalising. So this task we're going to share with you is called tilted squares, and it's a really beautiful one for demonstrating that links from the exploring and noticing into working systematically and then the conjecturing. So Charlie, here's our tilted squares problem.
Okay, so we might start, so we're assuming we're doing this with students who know how to work out the area of squares.
Yep.
And know how to work out the area of right-angled triangles.
Okay.
I don't think there are any other
Prerequisites.
prerequisites.
No, I agree.
And so you might start by saying, by noticing that students have no trouble working out the area of a 2 by 2 square.
Yep.
Or a 3 by 3 square. And of course, initially, you might do it by adding the squares.
Yeah, counting squares.
But actually, once you get to 4 by 4, 5 by 5, even 12 by 12, you don't want to be counting the squares, and you can, most of our students would know that that square's got an area of 144. And you might even go to even bigger squares. 20 by 20 square got an area of 400. Students might be able to tell you that without having to do the drawing, without having to count squares. Now, wouldn't it be nice to be able to have a similar strategy for working out the areas of squares when they're tilted? So far, Liz, you've only shown us squares on the screen in the usual orientation, where 2 of the sides are horizontal and 2 sides are vertical.
Yeah.
But let's imagine that to get from the vertex inside the blue circle to the vertex, the adjoining the vertex in the red circle, you've got to go across and then 1 up.
Okay.
So for example, 2 across and 1 up, or 3 across and 1 up, or 4 across and 1 up. Now, our students may be able to work out the area of this by boxing the shape in and working out the area of the box, taking away the area that is not wanted. So in this case, we've got a 3 across 1 up square. It's been boxed in with a 4 by 4 square, which has got an area of 16. And then you've got to take away the area of those 4 right-angled triangles. And students could do that by either working out the area of one of those triangles, multiplying by 4. But they could also even imagine shifting the bottom right-hand triangle onto the top left-hand triangle and making a 3 by 1 rectangle. And likewise, top right, bringing it down to the bottom left, making another 3 by 1 rectangle. So the 2 pairs of triangles could make 2 rectangles. Each rectangle would have an area of 3, altogether area of 6. And if you take 6 from 16, you get an area of 10. So students could do that, but it's obviously a little bit time consuming. So if we go back, wouldn't it be nice to find a faster method for working out the area of these tilted squares? So can we go back to the 2 across 1 up, please? So students might be encouraged to work quite systematically. You might share out the job between different groups of students in the class, get some working on a 2 across 1 up triangle, some on a 3 across 1 up triangle, some on a 4 across 1 up, 5 across 1 up, 6 across, 10 across 1 up. And when they put their results together, they discover that the 2 across 1 up has got an area of 5. 3 across 1 up has got an area of 10. 4 across 1 up has got an area of 17. 5 across 1 up, an area of 26. Now, if you haven't seen this problem before, you might want to stop and have a think about what's going on. So Liz, what did you notice about the areas that we were getting each time?
So I think each time we were getting one more than a square number.
So for 4 across 1 up, we got an area of 17, 1 more than 4 squared.
Yeah.
For 6 across 1 up, what would you expect?
I would imagine we'd get one more than 6 squared, so I'd get 37.
For 10 across 1 up?
I'd get one more than 10 squared, so 101.
So students could be coming up with that conjecture, testing it out.
Yeah.
So the systematic work, the recording, the bringing the results together leads to a conjecture that when I go n across 1 up, the area is going to be n squared plus 1. And different students could test out that conjecture on tilted squares of their own choice. And hopefully, if they've done this correctly, confirmation that this conjecture seems to hold.
Yes.
Now, what's nice about this is to be able to ask mathematicians, to the students, well, what do you think mathematicians would do next? And one question that mathematicians might ask themselves is, well, what would happen if it was slightly more tilted? So if it was 2 across 2 up, for example, 3 across 2 up, 4 across 2 up. And often the conjecture from students is, oh, for 4 across 2 up, it's going to be 4 squared plus 2. You're always going to get 2 more than a square number. And again, students could be delegated with the job of working out the areas of lots of tilted squares, which go across and then 2 up, gather the information together, and they'll discover that the area is not 2 more than a square number. Now, you know what the result's going to be.
I think it's going to be 4 more than a square number.
Right. So a conjecture needs to be amended slightly.
Yep, modified.
The modified conjecture can then be tested.
Yep.
We're trying to get students to work like mathematicians. They know how to work out areas of squares and triangles,
Yes.
and they're practicing that skill while at the same time working on a problem that's going to lead to a general result.
Yeah.
And the process of getting to the general result can be a little bit messy. It involves some conjecturing. What's nice about a conjecture is when you say a conjecture, you have a question mark at the end of it. You think that this is going to, you're not yet convinced, but you can try it out, you can test it out, you can do some more examples. After going across and then 2 up, you might go across 3 up.
Absolutely.
And again, it may not be obvious what the conjecture is here. 1 across and 1 up, we added 1 to square numbers, and then we added 4 to square numbers. Do we add 7?
They're going up in 3s,
go up in 3s. Some students may notice that 1 and 4 are square numbers.
Right, so we might conjecture they go up in 9.
And go up in 9. So again, what's nice about conjectures is all conjectures are valid. There isn't a right conjecture and a wrong conjecture. All are possible. At this stage, they are what we think might happen. It's a conjecture, we have a question mark. We test it out, we share out the job, people check, and indeed it will be 9 more than a square number. And all of a sudden, it looks like we're going to go across, and then when we go 3 up, the area is going to be 9 or 3 squared more than, and all of a sudden, we're getting to possibly conjecturing, well, what's going to happen if we go 5 across and 4 up, for example? And again, more conjectures, always the possibility of testing it out by drawing squares. And eventually, as either you know or you may have figured out by now, you could end up with Pythagoras' theorem. If I go A across and B up, the area of the square is going to be A squared plus B squared.
But how nice that students have discovered that for themselves. This is not something that's just been passed as something to remember by the teacher. They have been actively involved, and through the process of exploring, conjecturing, modifying, they have reached this generalisation for themselves.
Yeah, we sometimes talk about only do for students what they can't do for themselves. And here's an example of something they can do for themselves. And they can do it at quite a young age. Yes. Primary age students can work out areas of squares and areas of right-angled triangles. Yeah. Get plenty of practice at working out areas of squares and triangles. And in the process, discover Pythagoras' rule. Now, this is the third stage of a mathematical journey because for many students, this is not the end.
That's right.
This does not prove Pythagoras' theorem. It just shows that so far, all the examples we've tried satisfy.
Fitted our conjecture. Yeah.
But we don't have convincing, this is not sufficiently convincing to convince ourselves that this is going to work for all cases. And that will come at the end of our mathematical journey.
Absolutely.
But hopefully this captures the essence of and the value of conjecturing and generalising. Now, we have some guidance.
Yes, and if you'd like to find out more about conjecturing and generalising, if you go to the NRICH website, to the primary or the secondary teacher landing page, and you click on the second box, which is developing mathematical thinking, and scroll down to the conjecturing and generalising section, you'll see there's a link to our guidance in the blue box, where we've set out our beliefs about mathematics and mathematics teaching and learning, and how this might lead to some structural considerations for you in your classroom and your school, but also how you might facilitate in the classroom, so the nitty-gritty of those interactions to encourage your students to conjecture and generalise. We've also offered a little bit of a commentary on some NRICH tasks to further your understanding, and we've linked to some general further reading at the foot of this guidance. And just to go back to that top level page, we'd also like to draw your attention to groups of tasks. I happen to be on the secondary teachers page here, so you can see we've got groups of tasks for year 7 through to above year 11, and we've particularly chosen these to offer your students opportunities to conjecture and generalise. From here, we'll go into the fourth stage of the mathematical thinking process, and that will take us into visualising and representing.